and site validation of safety critical computer-based system of Indian nuclear power plants. He has published several research papers in journals of high impact factor like IEEE Transaction, IEEE Computer, ACM, etc. He has been invited as a chief guest, keynote speeches, session chair, and talk in many international conferences, short-term courses, workshops, and FDP programs from many IIT, NITs, and other institutions of national importance. Sir has a recipient of many awards like prestigious IEEE K Shankar Award, Publication Award, Group Achievement Award, etc. Sir has been also worked as a reviewer for several SCI index journals of high impact factor. He is a senior member of IEEE, life member of Indian Nuclear Society. Sir is a founder member of industrial coordinator of the proposed central dependability at IIT BHU. He is a panel of faculty assessment committee for Department of CSE IIT Roorkee to assess their research profile and give the recommendation. He is a member of editorial board of many reputed journals and guest lead editor of many special issues. He is supervising many PhD students from different IITs and NITs, and sir has also examined the PhD thesis of different IITs and NITs researchers. He is an expert member of Industrial Policy Formation of IIT Rupar, BOS of many autonomous institutions, and member of advisory board of many institutions and universities. He is an adjunct professor in BHU and IIT Gwalior. He is a reviewer and project collaborator of research proposal of Board of Research in Nuclear Science. He is also the faculty of Nuclear Training Center, Department of Atomic Energy, Government of India. He is interfacing with other countries like Russia, USA, France for importing nuclear reactors that are based on new technology. His research interests are in the area of reliability, safety, security of safety critical computer based systems. Sir has completed up till now 33 projects of Department of Atomic Energy, Government of India. He holds the 520 rank in India in the list of world scientists released by AD Scientific Index. So it's our pleasure, sir, to have you with us. So welcome, sir.
Thank you, madam, for your introduction. Uh,
Thank you, sir.
should I share my slides now?
Yes, sir.
Yeah. So please let me know, are my slides visible
Yes,
and
sir.
it
They
is
are
changing
visible and
also?
changing also.
Yeah, thank you. So I'll be talking on the machine learning in reliability analysis of safety critical systems. And we know like machine learning is a very upgrowing topic and widely used in many applications. So I'll be touching on one application that is on the safety critical system. So first, let us try to understand the motivation of this topic. So safety critical systems are those systems, the failure of which can lead to the catastrophic disasters, or even it can lead to the loss of human life. And hence, they do have very high reliability targets, and it is essential to to perform the reliability analysis for such systems to make sure that it is when it is going to deploy, it will perform or as per the intent and function, and it will also give the performance of high reliability as per the targets. So basically this topic I'll be discussing how we can do the reliability analysis of such kind of systems. And these systems are basically used in various life critical systems. For example, in nuclear power plants, in medical domain, in transportation, in defense, and this if I talk about the reliability, so the reliability of the system is defined as the probability of the failure-free operation of the system and up to the given period of time under certain environmental conditions. So one thing we can draw from the definition of the reliability is that it depends on the time, up to what period of time I'm talking about, and it also depends on the environmental conditions, because as I said, it is a failure free operation, means success operation of the system, and up to the given period of time means because nothing can be reliable for the infinite period of time. If I want to if I say anything is reliable, I'll also have to tell up to what point, what period of time we are talking about. In fact, the human can also not be reliable for the infinite period of time. So hence, it is very important that you have to tell up to what time you are talking about its particular reliability. And it also depends on the environmental conditions, because one product can be reliable under one operating conditions and may not be reliable under other operating conditions. So here in this topic, I'll be using the machine learning for reliability analysis of the safety critical systems. So now let us go through the quick agenda of today's lecture. So, introduction to reliability and background, this I have already discussed, but I will touch upon some of the mathematical concept related to reliability. Then the second one is the patrinets and modeling of systems. So patrinets is basically a mathematical and graphical modeling tool, and the concept was introduced by C.A. Petri, who was a German PhD scholar, and he introduced this concept to model the stochastic behavior of the system. So, if I want to define the processes, the kind of processes, basically, it can be broadly categorized into two. One is the stochastic process, second one is the deterministic process. And the stochastic processes are those processes the outcome of which cannot be 100% guaranteed, whereas the deterministic processes are those processes the outcome of which can be 100% guaranteed. For example, if I drop a pen, I can 100% guarantee it is going to fall down because of the gravitational force that is acting on it, and hence it is a deterministic process. But even human is not a deterministic in nature, so definitely all the man-made systems are not deterministic in nature. They are probabilistic in nature or stochastic in nature. Stochastic means there is some kind of randomness. So it may give uh, some abrupt behavior during the runtime, which we have not pretended. So I'll be discussing more about the patrinets, the working mechanism of the patrinets, and how we can model the system. Then we can discuss about the properties of patrinets and what are the various analysis techniques. Then I will be demonstrating one reliability prediction framework, in which I will be discussing what all the various phases that are required to be executed for the reliability prediction, in which we will also see how the machine learning can help us in different activities of that framework. And then we can conclude our session following by question and answers. So, as I said, the reliability basically it depends on the particular time, up to what period of time I'm talking about, and it also depends on the environmental conditions. So, if I talk about the mathematical representation of the reliability, so suppose x be a random variable, and this random variable represents the time to failure of a component. It means how much time a component will take to fail. Then the reliability of the component at time t will be given by Rxt is equal to, because as I said, the reliability is a function of time. So here I am in the bracket I am writing t, and it will be is equal to probability. Here p represents probability. Then definitely the value of this random variable must be greater than t. Why? Because x represent the random variable, which basically represent the time to failure of a component. Means this much time is being taken by a component to fail. Then definitely the time, this much time must be less than the target time. Must be greater than the target time, so that I can ensure that before this much time my component will not fail, and hence it will be reliable. So from the total probability law, I can equate it and I can write it down is equal to 1 minus probability of x is less than is equal to t. And what is x is less than is equal to t means my target time is less than sorry, this the random variable is less than my target time, and random variable basically it represents the time to failure of a component. Means my component has failed before time, so that is why it is not reliable. It is a failure probability. So I can write it down is equal to 1 minus failure probability, which is also a function of time. And sometimes this failure probability is also termed as unreliability. So reliability is equal to 1 minus unreliability, and both are probabilities. So from the total probability law, this equation holds well. So now there are, let us see some of the traditional methods for the reliability quantification. And these models are basically deterministic in nature. So one of the most prominent model is the reliability block diagram. And so this reliability block diagram basically it represents the logical structure of the component or of the system. So for example, suppose you do have a system like this, and in which you are having two components, let us say C1 and C2, and they are in series, for example. Then let us say the reliability of the component C1 is R1 and that of C2 is R2. Then the reliability of the overall system will be given by the series formula of the reliability, which is R1 into R2. Okay. And if the components are in parallel, we can apply the parallel formula. So basically, it represents a logical structure of a system with regard to how the reliability of its components affect the system reliability. Yeah, sorry. So now the next model is known as the reliability graph. And the reliability graph is also similar to the reliability block diagram, but it consists of two basic building blocks. One is the nodes, and second one is the arc. And nodes are used to model the link between two components, while arc are used to represent the component itself in the system. So if you see this figure, the left side of the figure, the left figure is, it represents the reliability graph. And here all the vertices are basically the connectors. These are the connectors, and all the arrows are basically components itself. So I can equivalently transform this reliability graph into the reliability block diagram. Okay. And so if you can see like V1 or V2, V3, V4, V5, all the V's are nothing but components. So I have written like this here. This is a component for V1. Similarly, this is for V2, for V3, for V4, V5. And all the vertex like A, B, C, D, these are the connectors. So for example, B is a connector of V1 component and V2 component. So I'm just connecting it like this. And now I can again use the reliability formula, because this 1 and 4 are in series. So if suppose it has the reliability as R1 or R2, R3 like this. So this segment, the reliability of this segment will be R1 into R4. Similarly, this one R2 into R5, and then all the three segments will be in parallel. We can use the parallel reliability formula to compute the overall reliability of the system. And now the third prominent model, which is very widely used in the safety critical applications, known as fault tree. It is very popular also, and it represents all the sequences of individual component failures which can cause the system to stop functioning, and it is in a tree-like structure. So, for example, if suppose I want to develop a fault tree of my laptop failure, okay. So here, for example, this is the laptop failure, and then I can deduce the reason. So it is a deductive approach. The reason could be, there could be the electrical failure, right? So it could be or gate I can apply, and here it can be the electrical failure. It could be mechanical failure. It could be electronics failure. And then further I can deduce, for example, in the electronics failure, there can be failure of ICs or registers. Similarly, in the mechanical failure, there can be, you know, might be some button is crashed or broken down. Electrical failure, maybe there is some problem from the socket side or electrical side, or an adapter is not working. And then I will keep on continuing reducing till I reach to the basic event, and I can then assign the probability of the basic event. And if the probabilities, if those basic events are basically uh, connected to the OR gate, then I have to sum up the probabilities to get the top basic event. For example, if I say a human is not able to see, this is the top event. The human is not able to see, or this is a blind, for example. Then definitely I will apply the OR gate. Then the basic event with left eye is not working and right eye is not working. So generally when basic event we define by circle. And let us say the probability of left eye is not working is P1, and probability of failure of that, or the right eye is not working is P2. Then because this is the AND gate, the probability of this blind will be P1 into P2. If there had been OR gate, it could have been P1 plus P2. And in this way, we can define the probability of the failure of the top event. And we know 1 minus probability of failure will give the reliability. And these basic event probabilities, basically we can assign using the statistical data, and where the machine learning and all those stuff is about to come. So the models that we have looked so far, the three models, the reliability block diagram, reliability graph, fault trees, these are deterministic in nature, and hence you can be solved using fast algorithms, assuming the stochastic independence between the system components. It means it assumes that if there is a system, and there are n number of components. Every component can fail due to itself only and not because of any other component. But in the real scenario, it doesn't uh, look like one component may fail because of the other component as well. And this stochastic independence we cannot model using the models what we have seen so far. And hence, to model these kind of complicated interactions between the components, we must use some other kind of models like Markov chains or patchy nets. So coming to the Markov models, the this model basically was proposed by Andrew Markov, who was a Russian mathematician in 1940s, and he introduced this model uh, to model the stochastic behavior of the system. And he thought that every system can be decomposed into the various states. For example, if a human is a system, it can be decomposed in several states like laughing, talking, moving, walking, sitting, going, and etc. And there could be the states can be broadly categorized into behavioral states and failure states. For example, if somebody has met an accident, it's a failure states. Otherwise, all the routine things will come into the normal states. And there will be a straight transitions from one state to another state with some probability, and that probability will depend from the statistical data, right? And if somehow I am able to find out the probabilities of all the success states, that if I sum up those states, those probabilities, it will give the reliability of the overall system. Similarly, or otherwise, if the behavioral states are many, I can find out the probability, the state probabilities of the failure states, and I can sum up those to compute the failure probability, and 1 minus failure probability will give the reliability of the system. And so coming to the basic building blocks, it basically contains the two sets. One is a set of states, and second one is a set of transition probabilities from one state to another state. Now let us try to understand some of the mathematical preliminaries which are important to use, which was we are going to use this in our model. So suppose there are the two states in the Markov chain. Let I and S belongs to that sample state. Maybe there are n number of states in which I and J are also belong to that particular state space. And let Qij be the transition rate from state I to state J. Then the self transition rate, that is Qi, it means the transition probability from state I to state I will be equal to minus, and we have to sum up all the transition probabilities from state I to rest of the states except I, right? So this formula is very important, which we are going to use when we'll be taking the case study and when we'll be trying to quantify the um, uh, reliability using the machine learning stuff. And then one term is very important, known as generator matrix, defined by Q, or the transition matrix. Basically, it is a matrix, so it contains rows and columns. And if you can write down row side all the states and column side all the states, then we can map from one state to other states. Each element will represent the state transition rate from one state to another state, and it is also known as a transition matrix or generator matrix. These are the preliminaries, just to understand when we will be really demonstrating how we can quantify the reliability. Now, coming to the battery nets, this is a very important stochastic modeling technique proposed by C.A. Petri, as I have discussed, who was a German PhD scholar in 1960s, and it is a very good graphical tool as well as mathematical tool. And why graphical tool? Because I can demonstrate the simulation of the system graphically, and hence it can be easily seen by all the observers that how what would be the real-time behavior of the system. And why it's a mathematical tool? Because it can use the mathematics to derive a lot of state equations to know much and more insights about the system. So it's the best communication between theoreticians and practitioners. And if you look about the what kind of modeling capabilities that it does, it can model all the kind of systems, whether concurrent systems, asynchronous systems, distributed, parallel, or whatever. So now let's quickly go through the history of this Patrinet. So as I said, the origination was from C.A. Petri in his dissertation, who was a German PhD scholar in 1962. And because that was the era where the people were trying to find out the model which is or to construct a model that should be able to model the concurrency and parallelism. And looking at the thesis, people were having a feel like this model will be able to meet that requirement. And with this with this objective, MIT USA conducted a conference on concurrent systems and parallel computation in 1970. And the conclusions were very fruitful. And then later on, again, they decided to strengthen the modeling capabilities of the model so that the various kind of attributes can be accommodated. And with this objective, again, they decided to meet after 5 years. So in 1975, MIT USA again conducted a conference on battery nets and related methods. And then uh, the demand also got increase in the industries. And looking at that demand, Germany started a course on general net theory of processors and systems. And then the people from the other domain also, they were eager and they were trying to understand whether the PatriNet modeling technique will be able to or they can model the applications of their particular domain. And with this objective, the France conducted a first European workshop on applications and theory of PatriNets in 1980. And then, the researchers were continue to strengthening the modeling power, for which different flavors of PatriNet started coming up. For example, if I want to work on the real-time system, definitely the timing information plays a very important role, and hence there should be a PatriNet where I can embed the timing information. And that kind of particular PatriNet is known as timed PatriNet. And first international workshop on timed PatriNet was conducted in Italy in 1985. There are some other flavors of patronage started coming up, but this is not an exhaustive list, but I wanted to touch upon just to make you understand from where it was originated to and what are the various important milestones through which it started gaining popularity. And if you look into the applications, they are able to model almost all kind of applications. Now, coming up the patronet's definition and the working mechanism of the patronets. So, first of all, let us try to understand the basic building block of the patronets. So, if you are able to see, there are the three big circles. Let me mark it is, for example, it is 1, it is 2, and it is 3. And these big circles are known as places. And then there is a rectangular block. Uh, it is known as a transition. So it can be either vertical or horizontal or at any angle depending on the convenience of the model when you draw basically. First, I'm just touching on the basic building blocks. Then I will be discussing what is the working mechanism of this model. So I'm using these places to for example. Okay, uh, now after transition there is an arc which can basically connect the place to transition or transition to place. So the next one is the arc. Okay, and there cannot be direct connection between places and between transition. That is very important to note. It can be the transitions can be connected through places, or places can be connected through transitions only. And every arc has a numeric number on it. For example, here it is 2, here it is 2, and here there is no numeric number. So if there is no numeric number, by default it is considered as 1. And this numeric number is known as weight of the arc. I'll be discussing the significance of the weight of this arc, but right now I'm just considering the basic building blocks. And then you are able to see the embedded circles inside the places. So for example, the one contains the two embedded circles, the place two contains the two embedded circles, and these are known as tokens. So tokens are basically inside the places, right? And now let us try to understand the significance of these basically basic building blocks. So suppose I want to model a very small chemical equation which you might have studied in class 10th or 11th. That is 2H2 plus O2 gives 2H2O. That is hydrogen oxygen reaction. And suppose I want to simulate it, I want to model this equation, right? So how I can do that? So here, this basically this Patrinet figure that you are able to see. It basically represents the left side. So let me write it down. It is the left hand side of the equation, and this is the right hand side of the equation. So these places are basically used to represent hydrogen, oxygen, and water, because there are the three entities over here which we are able to see in this chemical reaction. And hydrogen is diatomic, so atomicity I'm representing with the help of the tokens. So there are the two tokens in the hydrogen, two tokens in the oxygen, because oxygen is also diatomic. And now the important thing is this token distribution, or the distribution of the token, basically represents the state of the system. So if you talk about the state, basically is represented by the distribution of the tokens. Okay. And so here, if you are able to see, the state will be like 2 and 2 and 0. This is the state. And this is the left side, which basically. So because hydrogen contains 2 tokens, oxygen contains 2 tokens, and water contains 0 token. And now it has to convert into the water. So it means we need to change the state of this system. And to change the state of the system, the distribution of the tokens will be changed. So, but there is a rule by which the distribution of the token can be changed. And the rule says that at least one transition in the PetriNet model must be in enabled condition, right? So at least one transition must be enabled condition. Sorry, transition is capital T, must be in enabled condition. And what is the enabling criteria of the transition? It says that all the input places must contain sufficient number of tokens. So if you see, there is only one transition in this figure, and the input places are what from where see the arc with the places which are connecting from the input arc, and input arc are this and this. An input arc is defined, suppose any arc when it is terminating to any entity. For that entity, these arcs are input arc. And from where it is originating for that particular entity, that arc is output arc. So this is the output arcs, and these are the input arcs. So I said for the enabling condition of the transition, all the input places must contain sufficient number of tokens. So hydrogen place and oxygen place both must contain sufficient number of tokens. But what is the sufficiency criteria of the token? That will be governed by the weight of the arc, which is this. So here you can see the weight of the arc is 2, connecting hydrogen place and transition T, and hence hydrogen place must contain at least 2 number of tokens. Similarly, the weight of the arc connecting oxygen place and transition T is 1, and hence oxygen place must contain at least 1 number of tokens. And you can see here the eligibility criteria fulfills, and hence this transition is in enabled condition. And if this is in enabled condition, then it will fire. This transition will fire. And after firing, the movement of the tokens from input places to output place occurs. But how many tokens will be moved, will be removed out from the input place, and how many places will be deposited into the output place? That will be totally governed by the weight of the respective arc. So here, because the weight of the arc is 2, so the 2 tokens will be removed from the hydrogen place, and here the weight is 1, so one token will be removed from the oxygen place. But how many will be deposited into the output place? That will also govern by the output arc, the weight of the output arc, which is here 2, and hence only 2 tokens will be deposited in the output place after firing. So the next will be the next state will be like this. So you can see that 2 tokens would have already been removed from this hydrogen place, and 1 token from this, and only 2 is deposited. So one interesting fact is that there is no law of conservation of tokens, because if you sum of all the tokens, uh, the all the three tokens were moved out from all the input places, and only two tokens were deposited into the output place, and hence the it is governed by the weight of the respective arc. So now it has been converted into water, and now you can again look for the fireability condition or enabling condition of the transition. So you can see now it is not enabled because hydrogen place does not contain sufficient number of tokens. It should contain at least two number of tokens. Although the oxygen place contain sufficient number of tokens, but there is and logic, not or logic. And hence now this is known as the dead state, and because now the token distribution cannot change and hence the state cannot be changed. So this I can model like this. So this was the just the working principle of the uh, Patrinet. And one more point that we need to note is earlier the state was 2 to 0, and now after firing transition T, the state has been changed to 0, 1, 2 because it contains 0 token, it contains 1 token, and it contains 2 tokens, right? And this graph is basically, this is a graph because it contains node and arc. This is known as a reachability graph. And the reachability graph is very important because it helps in identification of the state space of the system. It tells basically how many states are possible inside that particular system. And yes, now let us try to understand some of the mathematical concept of the Markov chain. One Markov property that is important, and it says that uh, uh, the next state will only depend on the present state and it will not depend on the previous state. So what I can do is I can write mathematically that probability that my system is in uh, n plus 1 state is x, then given what is the probability that my system was in nth state, and it will not depend on the previous values. So I can write it down just like this. I can discard these values up to here. Okay. And so this is the representation of the Markov chain where these are the states which are represented by circle, and these are the transition probabilities. Transitions, basically we can assign the probabilities on these transitions to transit from one state to another. And now it is a random slide just to make you aware how the reachability graphs can be transformed into the Markov chain. So for example, there is a random reachability graph, and it contains suppose 1, 2, 3, 4, 5, 6, 7 places, and each place contains the token distribution is given here. So one place first place contain 1 token, second place 0, third place 0, fourth place 1 token, like this. Sometimes the token distribution is also known as marking. So marking is nothing but it is a state. Either you can name it as marking or state. It is same. It represents the token distribution. And suppose after firing T1, the marking is changed to this. After firing T2, it is changed to this, similarly like this. So it can be equivalently transformed into the Markov chain like this. So this is a state, and a state in the Markov chain is represented by circle. And all the transitions are basically these, and it can be a like frequency of the transition something. So this can be easily converted. And so this was basically the preliminaries, the preliminary knowledge about the PatriNet and about the Markov chain, which we are going to use in our basically prediction framework. So now let us discuss about the reliability prediction framework. So suppose you have been given a system and you want to calculate, you want to quantify the reliability. So first you have to create a PatriNet model. And we have already seen a small example, that is water reaction, how we have modeled using the PatriNet. And then this from the PatriNet, you can basically convert the PatriNet into the reachability graph, and from the reachability graph, you can create the Markov chain. So the second step is creating Markov chain, and then you have to apply the mathematical knowledge to compute the reliability of the Markov chain. So we will take a real case study and we will demonstrate how we can perform all these three cases. But before that, now we have to derive some important equation, which is we are going to use. So suppose the pi it is the probability that a component is in state I at time t, right? And where like I can be, as I said, it can be the failure states or it can be the behavioral states as well. And as t goes to infinity, these probabilities convert to the stationary distribution. Okay, so now this is a very important point. It says what does it basically what does it mean? If your system is very complex, it will take a long time to settle. For example, suppose you do have a small glass and just fill it with water and lift it up and put it somewhere. It will take little time to settle down. The water will take too little time to settle down. Earlier it will be little zigzag, and then after some period of time it will settle down. And suppose in place of this glass there is a big container, very big container, and suppose now if you fill this container with the water and then put this container, it will be zigzagging, and it will settle down after a long time. So for example, it will take a here very small time delta t, it will take a very large time t relative to this time. So what I mean to say, like if the complexity of the system is very large, or if your system is voluminous, it will take a longer time to settle down. So I ideally, what I have written over here, when this time goes to infinity, all the state probabilities converge to the stationary distribution. So this is the stationary distribution, and which can be computed by these two equations. These two equations are very important. Let me explain what does it mean. So the first equation is very simple. It says the sum of all the probabilities, state probabilities of the system at one time is always equal to 1. That is but obvious from the total probability law, right? And the second equation is uh, okay, we can derive it like this. For example, you know, just consider the same example, very big container. Probably this container is virtually at the size of your room. And suppose you fill it with water. So what will happen? Initially, the waves were very zigzags like this. Suppose this state is S0, and after suppose time t, after time t, it is approaching towards settling pace like this. So this is suppose now the next state is S1. So what is actually happening here? S1 is basically S0 into the transition probability from S0 to S1. Let us say P1. Okay. So let us say this transition probability is P1. Now again after till time T, the it is more approaching to the settling process, and now this state is S2. So now the S2 will be S1 into the transition probability P2. Suppose this is the transition probability P2, and similarly at the Sn, it has been completely settled down, right? So now after Sn, suppose further if you go, it will be in the next state will be Sn plus 1. So Sn plus 1 will be equal to Sn only because it has already been settled down, right? But the equation remain whole same, so I can write down Sn plus 1 is equal to Sn into Pn plus 1, for example. But this equation, this and state and this state is same. So I can write, and this is a stationary state, so I can denote it like this, and this is also equal to this. And because I'm dealing with multiple components, so I will be just taking the probability matrix of this, which is this equation, right? So now these two equations are very important, which we are going to use. And so now consider, let us take a case study of a communication module. And the communication module is like this. It's very simple system, for example. And suppose let me draw a figure. So suppose there are yeah, there are the field signals. There are so many sensors in the field. Okay, so I can write like there, these are the field, this is a field, and from the sensors the values are coming to the some embedded unit. An embedded unit contains the real-time operating system so that it can perform some real-time operations. And because we have to consider that any one this embedded unit may fail, so there must be one redundant embedded unit so that in the case of failure the other can take over, so both will contain the identical signals. And this signal is basically communicating. There is a switch which is communicating basically this signal to operator interface unit, or the display unit. So for the sake of redundancy, there are the two display unit, considering one can fail at any time. And also because the communication is plays a very important role, so here there will be the two LANs, LAN 1 and LAN 2. And it is transmitting to both the lands, and similarly it is transmitting to both the lands, and it is taking the data from both the lands, and it is also taking the data from both the lands. So here we have done the duplicacy at every level, right? The redundancy. Now so this communication plays a very important role, because if I want to compute the reliability of only this communication network, so that we have taken a case study of the communication module. So the protocol is whenever embedded unit sends a new packet, because every data is sent in the form of packets. So I'm keeping a count, a variable count, just to trace how many times it has attempted for these packets. And embedded units wait for the acknowledgement for time t1 after sending the packet. And if embedded unit receives acknowledgement before time t1, then packet send is successful because I cannot wait for the infinite time. For example, if I lift up a phone and I say hello, then definitely I will wait for the acknowledgement. The other person should reply hello. And if I don't get the reply, I will again say hello. If I don't get, I can say hello. But after couple number of times, after several times, if I am not able to get any acknowledgement, but I will feel that there is a loss in the connection, and I will then cut the call and I will retry. So I cannot wait for the long period of time. Okay. And so if embedded unit receives acknowledgement before T1, the packet send is successful, and I am keeping one variable that is a flag, which can represent whether it is successful or no. So it will change to the complement. And so if count is less than n, for example, if I have set that it should try only for 3 times, and so if count is less than n, here n is equal to 3, for example, and acknowledgement is not being received, then embedded unit retransmits the packet, and it will also increase the value of this count, keeping the trace that it is increasing. How many times I have sent the packet. Otherwise, the embedded unit terminates and the send process unsuccessfully. Where this will not change. And if T1 elapses after last data sent, this will be destroyed. So now if I want to, first I want to construct the PatriNet model, as I said, as we have seen in the reliability prediction framework. The first step was to construct a PatriNet model. So these are the places and transitions which I'll be explaining with the figure, because then you'll be able to understand in much more detail. So this PSRDY0 basically, so it represents that embedded unit is ready to send a packet. And I means if it is 0, embedded, it is embedded unit 1. If it is SRDY1, it will be embedded unit 2. Okay. So means it is ready to send the packet, and PDSR basically represent that embedded unit gets request from display unit to send the data. And hence these two eligibility criteria should be applicable. So this that is why I have kept the tokens in these two places. And now it is basically coming to the transition, that is TS0. And here TS0 represent that embedded unit sends the packet with a sequence number I. So it is very important because we have to, every packet has to be put a sequence number so that it can be ensured the correct sequence arrangement of the packets at the destination site. And once it sends a packet, I have to increase the count by firing this transition, right? And then after this, the token will be deposited, because This is the input place, and one interesting thing is all weights, the weights of all the transitions are one, and hence, so once it will fire, one the token will be deposited here, one will be deposited here, because as I said, there is no the movement of the token will be governed by the weight of the respective arc. So PS0S basically it represents the data packet of I sequence number sent. It means zero sequence number sent, and PSW0 it basically represents that embedded unit is waiting for the acknowledgement, right? And then TSW0. TSW0 is that your embedded unit has detected the timeout. This, and hence you have to again resend. So PT0 N0 is acknowledgement timer timed out for the data sent, right? And hence you have to retry again, you have to resend, and this will keep on continue till your value of na does not exceed to 3. For example, if I have kept only 3 iterations, and if it is sent successfully, then the token will fire, this transition will fire, this is the communication 1, and it will be deposited in this PR1R, and PR1R means it's the acknowledgement with sequence number I has received. Okay, and because the acknowledgement has received, and it was waiting for the acknowledgement, so it will be pulled up, and we have to declare that the packet has been sent successfully by putting a token in this PSUC, by putting a token here, right? And after firing this, also one token will be put here and one token will be put here, right? One interesting thing is that the left half of this figure is mirror image of the right half, because left half represents the communication from one embedded unit, and right half it represents the communication from the other embedded unit. And these why I'm sending the alternate the packet from the alternate embedded unit, the reason behind is because it also help in online testability, so that I can assure always that both the embedded units are working properly. And but in case after a number of trials here, if your again the packet is not sent, then this transition will fire, which is acknowledgement unsuccessful, and then the token will be deposited here, which will report that the packet sent was unsuccessful. Okay, so this is the entire patchnet model creation. And now basically the second one is we have to you know convert is yeah, second one is we have to convert it into the reachability graph. So now the main thing is we have to assign the model parameters, and how we have to assign the model parameters. From that, for that we have to use the machine learning algorithms to assign the model parameters, and so yeah, so basically this all the transitions, I told you that it depends on the statistical data. So using the experience of the existing systems throughout in whatever the systems are running, for example, this is being used in the nuclear power plant, so there are many systems from which we capture the data of many years and which are used as to derive basically the current delay of each and every transition. So every transition is having a delay, and using those algorithms basically, and using the Bayesian update, the delay was calculated like this. It is in the seconds. Every delay is in second. And then when you run this patterned model using the various tools, for example, there are the various tools which can solve the patterned model. For example, Petri or TimeNet. So these tools will basically help you to give the throughput of the transition. Throughput means the transition rate of every transitions, means how many number of firings per unit transition, how many number of firings per unit time of each and transactions. And this is the value that was obtained. And now we have to create the reachability graph. So now the reachability graph, for that we have to uh, understand the marking, that is the token distribution. So going back to this figure, you can see like at the initial time the tokens was in the three places. One is this and one is this, and yeah, only two places were having tokens. So you can see that marking, it is only containing only the two places contains the token, that is this and that is this, and all are zeros. So this is marking zero. And why it is tangible? Because there are marking are of two types. One is tangible and one is vanishing marking. So vanishing marking are basically when the transition does not contain any delay. So it can immediately fire without any delay. And then coming to this point again, after firing, because you can see this transition is in enabled condition because all the input places are containing sufficient number of tokens, because here also the weight is 1, and here also the weight is 1 of this transition. So this will fire, and it will deposit the token here and here, right? And then the weight, so here the token has been moved out from the earlier markings, that is, so one has been converted to 0, this also has been removed, and now it is deposited into the other places. And similarly, I can derive all the states, or I can derive all the markings accordingly. Okay. And for the sake of convenience, I have just mapped all these throughput values which are given. These throughput values, I have marked just as 0. I have mapped. So this is like lambda 1, this is lambda 2, this is lambda 3, for the sake of convenience, so that I can, when I will draw, I can I can save the spaces. Okay. Yeah. So now I can create the reachability graph, and we have seen how we can create the reachability graph. So this is the marking M0, and after firing of this transition T as 0, the marking is like this. And similarly, if you will draw one by one, you will get this reachability graph. And then this reachability graph can be converted into the Markov chain. And because this is marking is nothing but it is a state only, and states are represented by the circle. So it has been converted into the circle. And these all lambdas are basically transition rates from one state to another state. Okay. And then yeah, so now we have to do is we have to create a generator matrix. And as I said, the generator matrix, it contains the rows and the columns. So these are the rows and these are the columns in which we can write all the states. And going back, if you can see, there are only states M0 to M9. So there are the only 10 states. Okay. So just a moment. Yeah. Okay. So basically, uh, now here how I can fill the basically this each and every matrix. So what is this? It is basically the transition rate from M0 to M0 is this. The transition rate is from M0 to M1 is this. From M0 to M2 is this, and like that. Similarly, this, if I talk about this element, this is the transition rate from M9 to M0. Now let us say how we had filled this information. So if you see like the transition rate first from M0 to M1 is lambda 1, right? And there is no other transition from M0 to any other state. So you can write M0 to M1 is lambda 1, and rest of all are 0. I'll talk about this diagonal. Just hold a moment. First, let us see about the second, you know. So from M1, there are the two transitions. That is from M1 to M4 with lambda 11, and from M1 to M2 with lambda 3, right? So you can go and you can see like M1 to M2 is lambda 3, and M1 to M4 is lambda 11, and rest of all are zeros except this diagonal value. And for the diagonal value, we have to use the same equation as I had shown and I had discussed and asked you to note it down, because those equations I'm going to use further. So let me go back on the same slide so that you should be able to recall. Yeah, this one. So self transition rate is given by minus and sum of all the rest of the transitions. So the same formula is applied over here. Yeah. Yes. So here you can see the diagonal element is minus and sum of all the values, that is minus lambda 1. Similarly, this diagonal value is minus and sum of all the values, that is lambda 3 and lambda 11, and so on. Okay. So in this way, I'll be able to fill all the elements in the generator matrix. It is defined by Q. We have already seen it discussed, and it is also known as transition rate matrix. Okay, and now the transition probability. Now I want to calculate the transition probability from one state to another state. For example, if suppose this is a Markov chain, these are the three states. Let us say A, B, and C. So, what is the transition probability from state A to B? Transition probability from B to C. If there is a transition, or transition probability from B to C, like this. So if I want to calculate the transition probability from state I to J, it is very simple to calculate. It will be equal to the transition rate from I to J, and we have to normalize this transition rate. For normalization, we have to sum of us, we have to divide it by sum of all the transition rates from state I to rest of the state, right? So here k is not equal to I is important. And this holds when j is not equal to I. But if j is equal to I, it will be 0. So here we have just transformed the generator matrix Q into the transition matrix P, transition probability matrix. This is known as transition probability matrix. Okay. And now, so this the two equations that we were talking about that were more important when we have discussed about the steady state equations. One equation was, sorry, so one was this, that is pi I, sum of all the pi I is equal to 1, and this is known as sum of all the state probabilities will be equal to 1. And this will be like stationary distribution, that is uh, the final state is equal to just previous state into the transition probability matrix when in the case of a stationary distribution. And these two equations are basically being used over here. So one equation will be summing of all m0 plus m1 uh, plus I is equal to 0 to 9 is equal to 1. This will be the one equation, and the second equation is pi steady state equation is equal to pi into probability matrix. So this is a steady state equation because it's of all the states, and we have to multiply. This will be is equal to same into, we have to multiply the probability matrix what we have already calculated. And then these equations can be solved by various methods, analytical methods or simulation methods or Monte Carlo simulations, and we can find out the value of the state probabilities of all the states from M1, M0 to M9. So now one interesting thing is, it means we have found all the state probabilities of the system, and now we have to calculate the reliability. So here you can see these were the states, right? And these two states sorry, not this state. I'm just rubbing it. This state is basically leading to the unsuccessful acknowledgement. What does it mean? It means that you have already tried sending the packet couple of times, but it is not being sent even after retrying couple of times, and hence your ultimately your packet successful is failed. Your packet sent is failed. And similarly, this transition also says the same, right? So what we can do, because there are the two methods where we can compute the reliability of the overall system, because we have already calculated the state probabilities of all the system. So M0 to M9, these all the states, and basically if or other than these two states, all are successful states. So either you can sum up all the state probabilities of the rest of the states, that will give you the reliability, or uh, you can just sum up these failure states, and you can subtract it by 1 to compute the reliability of the overall system, because these two uh, probabilities are failure probabilities. When you sum up, it will give the cumulative failure probability of the system, and when you will subtract it by 1, it will give you basically the reliability of the overall system, right? So this thing we have done. So one is was M3 and one was M8, which was basically the failure state. So you can write down is the reliability, the 1 minus basically probability of M3 plus probability of M8, and because this is the failure probability, and 1 minus failure probability is the reliability, and so it gives basically the reliability of the entire communication module. So the interesting results we can get. And now the question is, okay, because your system is very voluminous, and this, the modeling of the battery net, or any, in fact, the modeling of any system is not so easy. Modeling requires a lot of effort and a lot of experience. So basically this quantitative assessment is very costly in terms of the resources that are required, in terms of expertise, and in terms of time also, and a lot of rigorous analysis needs to do, and we have to collect a lot of data, because machine learning is a data driven technology which basically depends on the data. More the data, the more will be the accuracy, and accuracy really plays a very important role if you are dealing with the safety critical systems. And hence, if your system is very large, it is advisable to decompose the system into the various modules. Try to identify the very critical components which are essentially to be analyzed with respect to the reliability, considering the importance, and what all the safety actions basically they are responsible for. And then in this way we can find out the reliability of the critical components. So that's all about the reliability computation or reliability quantification. So we have seen how we can model the system using the petri nets, for which we have really we have to understand the function requirements, and after that how we can convert into the reachability graph, which can easily find out identify the state space of the entire system, which can be later on converted into the Markov chain, which can be solved using a mathematical knowledge. And if I am able to somehow find out the state probabilities of the Markov chain probably just find out the failure states and do the negation of from one. It will give the quantification of the reliability. So in case of any doubts, I will now like to answer your questions.
Hello, sir.
Yeah.
This is Dr. Manali this side. Actually, I am really impressed by the way you had very lucidly you have explained everything, because reliability has never been my cup of tea and I've never actually tried to
Mhm.
understand about it. But I could really get very well the whole concept behind the prediction of reliability, particularly with respect to the mm,
Mhm.
safety systems, safety
Mhm.
critical
Yeah.
systems. Yeah. So actually, can you run through this Petri 2, because you have given three
Mhm.
phases for the calculation of reliability, one being the Petri net, another being the
Mhm.
Markov, and then finally the computation based on the probability of the failure
Right.
states. I could understand the probability of the failure state and then calculation of the reliability.
Mhm.
But somehow I am still not very clear about that Petrinet state to Markov state.
Mhm.
I mean, these two things. So, if you could please elaborate on this connection, like Petri to Markov, it will be really good.
Right,
Yeah.
right, right. So what I can do, I can, make a small example, and then I can show. Probably then you will be become more
Yeah,
perfect.
because I could understand Petri in isolation. I
Yeah.
could understand Markov in isolation.
Mhm.
But
Yeah.
then I could also understand the calculation after Markov.
Mhm.
But I could not understand Petri to Markov.
Okay. Okay. Fine.
Yeah.
Okay. So, for example, as I said, like there was, suppose this is your Petri net, and I'm just taking that example, and this is your transition.
Transition. Yes.
Okay. And it is basically, this is a third place basically.
Yes. Yes, sir.
Okay.
Yes.
And suppose I'm just taking so that everybody can understand, I'm taking the same example.
Yes.
Okay.
Yeah.
And now what is happening, here the weight was 2, here the weight was 1, and here the
Yes.
weight was 2, right?
Yes. Yes, sir.
So as I said, the distribution of the tokens basically represents the state.
Yes. Now I could understand the distribution. I could understand up to dead state also, because in the H2 nothing was left, but in O2 one token was left, so it was getting qualified. But as a whole, the it was not getting qualified. So you called that as a dead state. I got that also. Yes.
Uh-huh.
Yeah.
Okay, so the first state will be like this, like because
Yes.
it is a distribution. So this is 2, 2, and 0, right?
Yes. Yes.
And after that, it will be like this. If you have already understood, I'm not drawing now.
Hmm.
So it will be 0, 1, and
Yes.
2, right?
Yes.
So this will be the T, because after T it is basically firing, and this is nothing but this is the reachability graph basically.
Okay. Okay. Yes.
Okay?
Yes.
Yeah.
Huh. Huh.
So this is only the reachability graph. So if you will see the case study that you have taken, that we have taken,
Yes.
this was the PatriNet model. Okay,
Yes. Yes.
and which on in which in the there are only two places contains the tokens, right?
Yes.
Mhm.
Yes.
So basically, if you see, uh, this is the first the state, because and this is the only two states, only two places are containing the token. Rest of places are
Not
have,
containing any tokens. Yes. Yes.
okay.
Yes.
And when you go back, now let us see the next one. So this will fire, right? Because it is in
Has
enable.
the yes. Yes. It is enabled. Yeah.
Hmm. So the token will be moved out from these two places and will be deposited in these two places. Okay.
Okay, and that is how you can see the at every place there is a change in the
Right,
matrix. Yeah, in
right,
yeah,
right.
yes,
So these are nothing but these are these nodes basically, and
yes,
these nodes are this is only the reachability graph. Okay.
yes,
Mhm.
yes,
And which can be directly converted into the Markov chain. It is
yes.
because in the Markov chain, these states are represented by the circle. Okay.
Yeah, 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 yeah. Yeah, got it now. Yes. And one more thing, sir, the last thing. Actually,
Mhm.
you said that the Petri net that you have drawn, actually, they are the mirror of each other, because you were saying that as a backup plan, there was EU, that was one embedded
Mhm.
unit, and there
Mhm.
was another embedded unit, just in case one could not deliver, the other will take care of it, right? So
Right, right.
I was just trying to understand that
Mhm.
this transition, that means if a packet is sent and it's a failure, the
Mhm.
other EU will pick it up automatically and try sending, so that somehow either EU1 or EU2 will be able to successfully send the packet, or how?
Mhm. So this model is basically sending the packet alternatively. Okay.
Okay, yeah,
Alternatively, why? Because online testability feature has been incorporated. Now,
okay.
coming to what is online testability feature? Let me explain you
Mhm.
what actually it means. Okay, so basically, this is there are the two components. Suppose this is C1 and this is C2, and these are the redundant components. And suppose if one fails, the other one is able to perform its function. Okay.
Yes,
Now suppose the C1 components runs perfectly fine up to T1 period of time. Okay.
yes, yes.
But what will happen? Suppose now here it fails, for example. Okay. And now
Mm-hmm.
I want
Yeah.
to take the function of this C2. Okay.
Mm-hmm.
But when I put it online, it may be possible that uh, it it also it is not working that time. Why it is
Mm-hmm.
not working that time? Because although regular testing of the components are happening, for example, if this is testing, the testing period is 1 month, for example. Okay.
Yes, yes.
So 1 month, anyway, this is the online, so I don't need to test it
Mm-hmm.
continuously. And
Yes.
after 1 month, I am testing again. So suppose on the first of January, I have tested, right?
Mm-hmm.
Then the
Mm-hmm.
next test will be 1st of February. Next
Mm-hmm.
test will be 1st of March, right? Now
Mm-hmm.
imagine if it has failed on 15th of January, right?
Okay.
Just imagine.
Yes. Mm-hmm.
And imagine this C1 fails on 16th of January, right?
Mm-hmm. Yes.
Now we have to take the services of C2, but it has failed
Yes.
already on 15th of January, and the
Yes.
next testing was scheduled on 1st of February. So
Yes.
that time both the components will not be available at all.
Oh,
Okay.
yes. Yes.
So for this, either we go for the staggered testing that is out of the scope, which I will not touch much upon. So
Okay.
staggered testing will basically ensure that you have to test in such a way that you should compensate these kind of issues. Okay.
Yes. Yes.
Otherwise, the online testability feature means so why I was not requiring to test this C1 because it was continuously in operation, right?
Yes.
So
Yes.
why don't we do that? One packet I am sending from this and one packet alternate packet from this, then again
Mm.
from this, and then again from this. So
Ha.
this is
Ha. Ha.
also basically reducing the maintenance activity for which
Yes.
was schedule every month. We don't need to test at all because it is having the
In
online.
operation. In
Yes,
operation.
online
Yeah.
testability it is known as. So
Okay.
this feature is basically executed. So this model is basically for the online testability model,
Okay.
whatever the
Okay.
model that I have shown. Okay. But if you
Yes.
want to model it, keeping it the cold standby. This is known as basically hot standby. Okay, and
Okay.
if you want to keep it in the cold standby, the model will become different. So
Uh-huh.
that you have to ensure that once it fail, it will automatically taken away. So as I said, the modeling is plays a very important role. You need to really check the test the model because almost 40 to 50% of the time is basically spent on the modeling only. Okay.
Yes, yes, yes. Because that is the underlying framework and everything will depend upon that. Yeah.
Right.
Yes, yes.
Exactly.
Yeah.
Okay. So,
Thank you so much, sir. Thank you. Yeah. It was really very easily explained. I really
mhm.
appreciate. Yes, sir.
Mhm. Okay, thank you. And
Thank you,
one
sir.
more thing, like if you this is because I think the audience are of machine learning. So what
Mm-hmm.
I can do, I can share some of the link. I have made some of the video lectures also to explain conceptually and various case studies also. So
Okay.
you can go through that, and you can also subscribe it for the future videos also. So I'm just the interested people who would be uh, willing to understand the various case studies on the machine learning or different kind of techniques. In fact, the Python programming also and all those stuff how we can perform.
Yes,
The
yes, yes.
interested people can take a
We'll
note
be
on.
interested definitely. Ujwala madam and Swati madam, can you please do the needful?
Yes, ma'am. Yes.
Yeah, yeah.
So I
Please.
have already in the comment box. I have already sent a link, so you can note it down. You can subscribe. Whatever the upcoming videos will be coming, you can go through
Yeah.
that.
Oh, definitely,
You
sir.
can, Ujwala Swati, you can please pick up the links because I am
Yes, ma'am.
actually on my mobile. I'm connected on my mobile. So, like, I may not be able to work more on it. So, if you could please do it
Right,
for
ma'am.
me, I would be really thankful. Yeah.
Yes, ma'am. So, participants, any questions?
Sir, can we use the
Sorry,
time
please.
series data for
Pardon?
this one?
Pardon?
Can we use the time series data for this one?
Time series data.
Yes, sir.
Data you can use whatever the required data. Only the data, the uncertainty in the data is very important. As I said, data has to be very proper because if your data will contain uncertainty, it will lead to the inaccurate prediction, and you cannot afford the inaccuracy in such kind of systems. So for which basically the machine learning algorithms plays a very important role because it requires a lot of data for the training purposes, and a lot of new data is coming on. And you can use the data whatever the objective of your problem is, but the data uncertainty you have to be very careful.
Okay, sir. Thank you.
Yeah.
So, any other queries, guys? Participants? Okay, if there are no queries, then I would request Swati ma'am to propose a vote of thanks. Sushil?
Okay. Sushil, sir.
Sushil, the online memento, please.
So, Lalit sir, on the behalf of information technology, I would like to thank Dr. Lalit Kumar Singh, sir. And, sir, I really appreciate the way you have explained this topic. So, it's thank you very much for your and, sir, we hope some more. Hello,
Okay,
am
madam.
I audible, sir? Am I audible?
Yeah.
Ah,
Thank you, madam.
yes.
Yeah.
Sir, again, I would like to say you the thank you. On the behalf of information technology, I would like to thank Dr. Lalit Kumar Singh. And sir, I really appreciate the way you have explained this topic. So we hope some more interaction with you in future, sir. Thanks a
Yeah.
lot, sir.
Thank you, madam.
Sir, this is Ujjwala Gavande.
Yeah.
Sir, I would request you if you could come to YCC once and deliver one offline session so
Mm-hmm.
that we can have a good connection between the BARC and the YCC people, and
Sure,
we
madam.
can look for some future work in
Mhm.
collaboration.
Yeah, sure, madam, sure. We
Right,
can
sir. Right,
explore.
sir. So, yeah. So I am having your contact details, so we will definitely in touch with you, sir.
Yeah, sure, madam. Yeah, thank you.
Okay, sir. Thank you so much for delivering such a nice session, sir.
Yeah,
Thank you.
thank you.
So, participants, thanks for joining, and good night. See you tomorrow at 7 p.m. So, you can leave, sir. All of you can leave, please. Thank you. Thank you, guys.
Thank you, ma'am.